This is the first lecture. I'm using slides here because the first lecture will be focusing on some conceptual introductions. While in the future, if there are more equations, I will have to write on the digitizer whiteboard, something like that, to do some calculations and equation derivations. But first of all, let me introduce myself. My name is Cheng Huang. I got my bachelor degree from China, from Zhejiang University in China, which is very close to Shanghai. And I chose the topic, actually chose a major of electronic science and technology, microelectronics. The reason I chose this topic is because when I was in high school, I was into overclocking my own computer. I actually worked on some hardwares with my dad to desolder some capacitors and change it with higher quality, lower ESR equivalent series resistance ones, try to improve the power module of the motherboard, and then try to crank up the CPU speed from, say, 333 megahertz to 500 megahertz, something like that. And it is very effective. So it really impressed me why changing those chip capacitors will make a significant difference, and I would like to figure out what is happening there. So that's why I chose this topic to work on some hardware or microelectronic related topics. And then I didn't actually get my answer when I was a bachelor student until I graduate. Well, not until I graduate, but until I went to Hong Kong University of Science and Technology to pursue my PhD, where I chose to work on switching power converters, which is very close to the topic. So there I learned how a DC to DC converter voltage regulator works, and then I finally figured out why changing those capacitors will make such significant impact. It is basically because of the voltage ripples. But yeah, that's why I chose the topic here. And then during the time when I was a PhD student, I joined Broadcom Corporation as an intern, international intern. So where I designed some voltage regulators, linear regulators, boost converters for system chips in Broadcom for about half a year actually. And then after that, I went back to Hong Kong University of Science and Technology and then graduate. And then after that, at that time, I was very into animations and games, especially those from Japan. So I really would like to experience life in Japan for, say, a few years. So that's why I decided to go to Keio University in Yokohama in Japan, very close to Tokyo, to live there for about 1.5 years. So where I work on some wireless power transfer system projects, which I think is very interesting, to wireless charging, in this case biomedical implants, but the technology is pretty similar to like the wireless charger for your phones, but the power rating is very different, much smaller power ratings for biomedical implants. But at that time I also traveled a lot in Japan, and it was really fun living in Japan. And then during that time I got the return offer from Broadcom. Then they changed their name from, you can see the corporation and limited, and then the logo is different too, because there was an acquisition going on back then, and Broadcom Corporation was acquired by AlphaGo, which headquarters in Singapore, so it becomes an Asian company, and the name is also changed to Broadcom Limited. They somehow kept the name of Broadcom, not AlphaGo, because maybe it is a more well-known brand. And I worked there as a full-time IC design engineer to develop next generation smart network interface SoCs for servers in data centers. And also I also work on some Apple projects, because Broadcom sold chips to Apple. I worked on the control chips for next generation Apple products, for example iPads and iPhones, etc. And then at that time I got the opportunity to come to Iowa State University to work on some researches again in academia. So I joined as an assistant professor here in 2018 in January and until now. So what is electronic or electric circuit? Well, there is a common confusion between the two terms electric circuit and electronic circuit. Well, there is no clear boundary between the two, and in fact, different people from different areas will have different understandings. And even for example, in the Iowa State University, the department is called Electrical and Computer Engineering. But in the university where I got my PhD, it was Electronic and Computing Engineering. So, and for the one that I did my research in KU University, it was Electrical and Electronic Engineering, so triple E. So there's no clear boundary between these terms, but to my impression is that electric circuit is with like a higher voltage, higher power. For example, electric cars that has a relatively high voltage, say 400 volt battery to drive the electric vehicles that consumes kilowatts of power. But for electronics, usually, for example, your smartphones are electronic circuits, laptops, etc. So that has lower voltage and lower power. But there's no clear boundary between the two. There's another saying that electronic circuits will involve more control, while electric circuits, for example, appliance, we have less control. But I don't think this is completely true because, for example, the control system in electric cars are very complicated, right? So anyway, so electronic circuits can be in the form of hardware. So what you're seeing is some board level electronic circuits. On the left hand side is some logic boards from the iPhone X, which is outdated, but you can see that it is packed with a lot of chips here, and some passive components. And on the right hand side is the motherboard from a desktop computer. So a lot of sockets there, and the processors and the chips are consumes more power. Anyway, these are some hardware logic boards. These are rigid printed circuit board, which is traditional printed circuit board like this, and it can also be, for example, in the form of some flexible printed circuit board like these. It's flexible and can be used in some moving parts or that has to be flexible places. It can also be in the form of these are board level circuits, and it can also be inside the chip. For example, my major is microelectronics, and I work on power management integrated circuit. So integrated circuits are also circuits. So the design procedure is basically so you design schematics using analysis, mathematical analysis, and also design it in the software called, in this case, Cadence. You draw those transistors, resistors, capacitors, for example, and then do simulations using software. And after the design is validated using simulation to verify its performance, its function, and if it meets your expectation, then you need to fabricate the chips. And then you draw the physical layout. So these are what you see, different colors, actually those different layers on the chip. So these yellow ones are the pads that bring the internal signals out. And then you can see that there are different colors which has different layers on it, different metal layers and transistors, etc. So this tells the manufacturer, for example, TSMC, what layers to use to fabricate different devices. And then this kind of file will be sent to the foundry, for example, TSMC, to fabricate a chip. And the chip come back like this. And then in order to use it, you need to put it into the package. So this is an IC package using bonding wires. So those pads, you need to bond it out to the pins there, and then you solder it onto the printed circuit board, right? It can also be in the form of, for example, the schematic you see here. It can be hand-drawn circuit, or usually during the analysis and design stage. And after that, you can produce a nice-looking schematics to be used, for example, in the datasheet or in the service menu, for example. So it looks neat and very clear. So basically, this is a power supply, ATX power supply. But in this course, because this is an entry-level course, so what we are looking at will be some basic circuit consisted with resistors, capacitors, and inductors, and it will not be complicated. And this is just to prepare some knowledge in the future in order to learn more complicated circuits. And then in this lecture, we will learn some systematic analysis method, for example, KCL, KVL, and other AC and DC circuit analysis methodologies to analyze a simple circuit. So in the future, with those knowledges, we will be able to look at more complicated circuit. Okay, so there is a common misunderstanding that, for example, if you're a computer student, some students may think, well, the 201 is not important because it is talking about hardware, and I'm a computer engineer and focus more on the software. But this is not true because nowadays the system is so complicated that it is very difficult to separate hardware from software or software from hardware because they work together. For example, if you need to design some products, for example, using some Arduino or Raspberry Pi to control some kinds of systems, and in the end, you need to drive some hardware to actually do something, or use some hardware to actually monitor something, right? So in the end of the day, you will need to program it to work with some hardware components, and then you need to connect it, and then need to worry about its power consumptions, etc., the voltages, etc. So you will need to have some hardware knowledge in order to do the circuit, in order to do some project like this. Well, on the other hand, if you're a EE student, well, software is still very important because, again, it is not easy to separate hardware and software. For example, we were talking about chips, and I worked in the VSI, the microelectronic area, to design some chips. But chips will rely on a lot of software to operate, especially for digital circuit or big signal circuit. For example, CPUs, memories, etc. Those chips have billions of transistors, and it is not possible to design billions of transistors by manually. So for digital circuit, usually they need to use some kinds of hardware description language, Verilog or VHDL, to describe the behavior, and then do a simulation, and then use the software to generate the layout automatically, basically the physical layers on the chip, and then fabricate it and become a chip like this. So even if you are a hardware design engineer, you will need to use some kind of software to develop a chip, and you may need to even write some programs to describe the behavior of the chips. To either actually is one of the design procedure of the chips, or to speed up the simulation, for example, in a very large scale system, even if it is analog circuit. Because, well, I am a analog design engineer. Basically, we deal with analog signals, not digital ones. But even with analog signals, when the system is growing bigger and bigger, doing a simulation verification is very difficult. So we need to reduce the time spent on simulations. What we need to do is to use Verilog, system Verilog to describe the behavior of a certain building blocks. And then in that case, you can replace the real circuit with some behavior programs in order to speed up the system simulation, which will reduce the time to the market. For example, you may need to spend weeks to do a simulation in a system level, but with behavior languages, it may reduce the time to only, say, 1 day or a few hours. So keep in mind that even if you are a computer student, hardware is very important, and vice versa. Now, let's discuss some basic circuit quantities. So basically, we are trying to look at electric charges. There are positive charges, we call it proton, and negative charges, we call it electron. And for example, if you're looking at the battery, the chemicals inside the battery separate those positive charges and negative charges, right? So the positive terminal, the battery has a positive terminal. basically there are positive charges accumulated there, and there is a negative terminal. So the negative charges are accumulated there. If you connect something between the positive and negative charges, because they try to meet with each other, so basically the charges will flow through, for example, a resistor or light bulbs, so that you can actually do something. And then the charge is moving along this loop, and then separated again by the chemicals inside the battery. And then the moving charges forms current. So there's a voltage across the positive and negative terminal. So we have voltage there. And when the circuit loop is closed, there will be charges flowing through the line. So this is basically charging, this is basically current. And then during the process, there will be associated power or energy consumed or generated. Before going into the quantities, these are some prefixes that we will be using throughout the lecture. On the left hand side is the larger ones, larger prefix. So it is added in front of the actual unit. For example, tera, giga, you see those a lot when you look at, say, storage devices, hard drive, or SSDs, etc. So terabyte is basically 10 to the power of 12 bytes, and gigabytes, for example, and mega 10 to the power of 6, and kilo 10 to the power of 3. So basically 1 kilovolt is 1000 volts, right? And then on the right hand side is those smaller prefixes. For example, those in the red square are used quite a lot. For example, when we look at capacitors and inductors, for example, capacitors, 1 farad is a very large capacitance. So farad is a large unit. So that's why when you look at actual circuits, the capacitance is much smaller. For example, femtofarad in femtofarad, picofarad, nanofarad for like integrated circuit, or like microfarad in your motherboard, etc. So for example, micro is 10 to the power of minus 6, nano is 10 to the power of minus 9. So you can convert different prefixes easily. So for example, 1 volt is, if you write it in millivolt, in the millivolt with milli prefix, then it will be 1000 millivolt. Milli is 10 to the power of minus 3, so it cancelled out with the 10 to the power of 3, which is 1000. And if you want to write it in the micro prefix, then it will be 10 to the power of 6 to cancel out the 10 to the power of minus 6. And then, for example, 1 millivolt is basically 10 to the power of minus 3 volts, right? So, first of all, what is voltage? Well, the definition is very difficult to understand. So 1 volt means you need 1 joule of energy or work to separate 1 coulomb of charge. So it is very difficult to understand what it means. So let me try to explain it in some easy to understand language. So first of all, there are symbols and units. So for voltage, the symbol is V. So when you write equations, basically you write V there. And there is actually a unit to describe the quantity. For example, 1 volt, 2 volts, 1 kilovolts, right? So the unit is usually written after the number to describe the quantity, while symbols are used to write equations to describe what you are trying to calculate. So in this case, these equations is using symbols. Volt equals to dW, which is the amount of energy required to separate the amount of charge, which is Q. And then it is in the form of coulomb. Or you can write in the quantity form, which is 1 volt equals to 1 joule of energy per coulomb of charge. So 1 joule of energy to separate 1 coulomb of charge. You get more. You will have more idea when you're actually doing the calculations later on. So then, what is voltage? Well, sometimes we call voltage potential, because it has potential to do some work, right? For example, if a stone is lying on the ground, assuming the ground is the lowest point, so in that case, the stone has no potential to do anything. So it cannot be used to break something because it is lying at the lowest point, right? In order to do something, you need to lift it up. So in that case, a human being is spending some energy or work to lift the stone up above the ground. In that case, the stone will now has potential to break something. So it has, in the electric world, it has voltage. Or if you look at an atom, for example, I'm using a silicon here, so there are 14 protons in the middle and there are 14 electrons surrounding it. So by default, there's no potential because the numbers are equal, right? Just like a stone sitting on the ground. But in order to make it do something, you need to separate the charges. So in a battery, it is actually the chemicals inside the battery is doing the work, so that the positive charges is accumulating in the positive terminal and the negative charges is accumulating at the terminal. So with those chemicals inside the battery, chemical reactions inside the battery, you will be able to do something. You have potential to do something because there is a voltage there. And then how much energy to separate 1 coulomb of charge actually depends on the depending on the material or chemicals inside the battery. So for example, if you're looking at nickel metal hydride batteries, it usually has 1.2 volt. It means that it actually requires 1.2 joule to separate 1 coulomb of charge with this kind of chemical. And then lithium ion battery, the nominal voltage is about 3.7 volts. And it can be different forms, say the old school phone batteries or the 18650 lithium ion batteries to use in, for example, your laptops or a Tesla electric vehicles. Then there are some different other forms too. And then for lead acid cells, one cell is about 2 volt. And then for a car battery, for example, there are 6 cells connected in series generating 12 volt to start your car. So that is voltage. And then the current is a little bit easier to understand. It measures the flow of charges in a certain amount of time. For example, 1 amp basically is the flow of 1 coulomb of charge in 1 second. Or if you are equations, it is the I is the current symbol, I is the current symbol, and the charge symbol is Q, and the time symbol is T. And then if you want to express it in the quantity way, in terms of quantity, so it is 1 amp equals to the flow of 1 coulomb in 1 second, right? And then, for example, if you have a alkaline battery, 1.5 volt battery, you have positive terminals accumulated at the positive terminal, and you have negative charges accumulated in the negative terminal, right? But if you don't connect it, there is no current because no current outside the battery because you don't have a loop. But if you connect something, for example, a resistor, then because positive and negative charges try to attract each other and try to neutralize it. So if you provide a path, the positive charges will go to the negative terminal to neutralize with the negative electrons. Well, actually, in fact, it is the electrons flowing backwards, but it is easier to understand using positive charges. So the positive charges move from the positive terminal and then go to the negative terminal to neutralize with the electrons. And then after that, the chemical inside will separate those charges again and then accumulate at the positive terminal again. And then there will be continuous current flow in this case. So power. Power is, well, a very well-known term that we use a lot in our real life. So we know that in order to do something, you need to use energy. And then power is basically the measure of energy used or generated in a certain amount of time. So the higher the watt number, the higher the power, for example, for your appliance, the faster it used up energies. And the energy is in the form of, in the unit of joule. So it is very easy to understand that power is dW dt. W is energy, dt is time. The higher the power, the faster it uses up energies or generate energies, for example, a generator. And then this is the equation, power equals to the energy, dW, divided by dt. dt is the time. So in terms of quantity, 1 watt is basically 1 joule per second, using 1 joule per every second, right? And then if you are interested in say what is the energy consumption rate of your appliance, you can go to some website and search on internet to take a look. So I'm not going to that. And we know that P equals to dW dt, right? If you add dq to the numerator and the denominator, you can write it in the form of dW dq times dq dt. And we know that dW dq, what is dW dq? dW dq is voltage, right? And then dq dt is basically current, the amount of charges flowing in a certain amount of time. So this is voltage times time. So this is a very widely used equation, P equals to VI. Or I can say that actually this is the most important, most valuable equation of the day, P equals to VI. It is more often used compared to, for example, dW divided by dq for voltage or dq dt for current. So if you write in quantities, because we have this equation, and then the unit for power is watt, the unit for voltage is volt, the unit for current is amp. So 1 watt equals to 1 watt times 1 amp. So this is a quantitative form. You will get more idea later on when you're familiar with circuit analysis. So energy is basically the opposite when you use power and time to describe it. So energy is the accumulation of power over time. So for example, if power is a time variant component, and then you need to integrate it over time, and then say in this case 1 joule is the unit of energy, and then W is the unit of power, S is the unit of second, which is time. So if you describe it in a quantity equation, it is 1 joule equals to 1 watt per times 1 second. So if you have a 1 watt device and then you use it for 1 second, so the energy used by that device is 1 joule in 1 second. And if the power is a constant number, then it can be simplified as the multiplication. So W equals to P times T, if P is a non-time variant component. So you may have a question. We know that the energy unit is joule. So how much is 1 joule? Well, 1 joule is actually not a very large number. So 1 joule energy can be used or generated in different forms. For example, if you use it to transmit data, 1 joule can transmit about 25 megabytes of data if you're using, for example, AC Wi-Fi. Of course, the actual situation is different depending on lots of variants, but this is just some estimation. If you use energy to lift an apple, 1 joule can lift an apple up to the height of 1 meter. So, although joule is the basic unit of energy, but actually if you're talking about a much larger scale of energy, you can use some other unit. For example, kilowatt hour is another commonly used unit for energy. For example, the Ames electricity rate was 11.8 36 cents per kilowatt hour. So how to convert kilowatt hour in terms of joule? Well, actually it is pretty straightforward, because 1 joule equals to 1 watt times 1 second, right? And then 1 kilowatt hour, kilowatt is 1000 watt. Hour is 3600 second. So 1 kilowatt hour equals to simply 1000 watt times 3600 seconds. So which means that it is 3, 6, and then 5 zeros. Oops. 5 zeros joule, right? And then if you write it in a more scientific way, it is 3.6 times 10 to the power 6 joule. Joule. Then we know that 10 to the power 6 is mega, right? So it is 3.6 mega joule. That is pretty straightforward, and we know that kilowatt hour is a very large number of units to measure, say, how much energy you used up during this month, for example, to pay for your electric bills. And then another commonly seen energy unit is amp hour or milliamp hour. If you look at the smartphone, the battery, there is a number on it that says the capacity is something milliamp hour. For example, an iPhone X has 2760 milliamp hour. So how to convert it into joule? Well, we know that 2760 milliamp hour is we try to convert it into the basic units first. So it is 2.716 amp times hour has 1 hour has 3600 seconds, right? And this becomes 9777 amp times second. But 1 joule is 1 watt times second. So what is amp second? Amp second is actually you need to actually add some components here to convert it into energy, because something is missing here, right? So 1 watt is 1 volt times amp. So actually missing the volt here. So we can actually estimate the capacity of the battery in terms of energy if you have the information of the voltage. So we know that for a lithium-ion battery, the nominal voltage is 3.7 volt, but of course the voltage fluctuates depending on the situation, depending on the actual conditions of the battery. If it is fully charged, the voltage will go up all the way to, say, 4.2 volt. If it is almost used up, the voltage will drop to, for example, 2.8, 2.9 volt, 3 volts. But we usually use the nominal voltage of 3.7 volt in order to calculate, because it just makes things easier. So in that case, we have 9777 amp times second. We need to add the volt here, so multiply by 3.7. It gives you about 3.6 times 10 to the power 4 joule, which is 36 kilojoule in this case. So that's pretty much what I would like to discuss today, some basic quantities